Let's introduce the concept of differential cross-section. Consider the following scenario of scattering. The element of solid angle into which the scattering occurs is given by d omega, the element of the area divided by the radius squared. The element of the area defined on the sphere of radius r will be given by, on one hand, the side of this triangle r sine theta, and whatever rotation by azimuthal angle, we're using spherical coordinates, phi, and the element r times d theta. So we can write that the element of area dA will be given by r times sine theta times d phi, azimuthal angle, times the element length r delta theta. In other words, the element of solid angle in spherical coordinates becomes simply sine theta times d theta, the pole angle, times d phi, the azimuthal angle, and r squared is cancelled out. Next, let's consider of number of scatterings into the solid angle element d omega. We know that it will be given by the number of incident projectiles times the target density times only fraction of the probability d sigma, which relates to all scattering that will happen into the solid angle d omega. This differential of the cross-section into the solid angle element d omega is simply given by d sigma over d omega, which itself is a function of the angles, polar angle and azimuthal angle, times the solid angle element itself. As far as the total cross-section of the process, it is found by integrating over all solid angle, and it's simply d sigma over d omega times d omega. This derivative here is known as the differential cross-section. In terms of angles theta and phi, we can rewrite this integral as integral from 0 to pi of d theta sine theta, and integral from 0 to 2 pi of d phi of the differential cross-section d sigma d omega. The differential cross-section gives us an insight into the nature of the interaction. We can demonstrate it as following. Consider the same scattering problem. A particle coming with an impact parameter b towards the target, and it scatters into angle theta. Now, if the impact parameter is different, then the angle will also be different. We can estimate the solid angle element for azimuthally symmetric scattering, this ring that's given by the ring of impact parameters. So we can write directly d sigma over d omega. D sigma is simply this area of this ring that will be sampled by the beam, which is given by 2 pi b times dB, whereas the element of the solid angle is given by 2 pi sine theta d theta. Again, we took advantage of the fact that phi goes from 0 to 2 pi, which we simplify to get b over sine theta times dB d theta. Since the differential cross-section is a positive quantity, let's take absolute value of dB d theta. So using information on how impact parameter b depends on theta, we can substitute it into the differential cross-section expression and find total cross-section. Another question we would like to consider is how the differential cross-section depends on the reference frame. In other words, if we have differential cross-section measured in the center of mass versus differential cross-section measured in the lab frame. They are not going to be the same as was in the case with the total cross-section, because now we have angles in the center of mass not equal to the angle in the lab frame. In other words, if you consider the number of scattering events that will happen into the solid angle element, the omega, it will be given by the number of incident particles times the target density times the differential cross-section times the element of the solid angle. Now, this number of events will be independent from the reference frame, which means that this quantity here will have to be the same for either center of mass reference frame or the lab frame. Thus, we have that differential cross-section in the lab frame times the solid angle element in the lab frame is equal to differential cross-section in the center of mass frame times the solid angle element in the center of mass. We know that polar angles or scattering angles are not the same in the two different frames. However, azimuthal angles are the same. So what that means is that the solid angle element is going to be given by sine theta d theta. This differential here we can further simplify to write differential of cosine theta. Using this information, we can now write differential cross-section with respect to lab frame given in terms of differential cross-section in the center of mass frame by the ratio of the following differentials: d cosine theta in the center of mass divided by d cosine theta in the lab frame. Again, to avoid negative probabilities, we take the absolute value here. We have previously found the relationship between theta lab and theta in the center of mass. Using this information, we can evaluate this derivative here, which you can further simplify on your own.